Hi, this is the third and last of the three videos I've put together for you for Unit 4 on networking, and we're coming into the home stretch here. We are going to, in this video, learn how a network talks to another network. So how you, at your computer or on your phone, can send a signal through your network that goes out to a wider area network. In most cases, the internet. We have to learn a little bit more about protocols in order to do this, so let's get started. Most local area networks today are implemented via a switch. Now, remember in our last video we talked about network topology? Instead of stringing a lot of wires between the computers, or having every computer wirelessly connect with every other computer, they communicate with a device, one central device for each local area network, called a switch. What's a switch? It's a network device that takes packets of information from input devices and sends it to the appropriate output devices. So the connections are all inside the switch. You can think of like there being a data bus inside a switch, but it's really small and compact. And the switch itself generally has a CPU in it. The switch has some processing that it can do to intelligently route things from one location to another and so on. Switches generally function as their local area network's domain name server and DHCP server. They've got a lot of smarts in them today. So a router is a network device that connects one network to another network. Now, a router has to have at least two, maybe more, network addresses, one on the local area network and one on another network, typically the internet. Routers are responsible for examining data from the local network and determining when it needs to be sent to the external network, and similarly for taking incoming data from the external network and serving it to the appropriate local machine. Now, most of the time, homes and small offices today have a wireless router. I've got one in my home. You may have one in your home. Your school probably has several. It acts as a wireless access point, meaning a place that can handle the physical signals being sent through the airwaves. It also is not only a router, but it's the switch for the local devices to connect in a local area network. It houses the DHCP and DNS server functions, and then it connects to the internet via cable or satellite or some other broadband medium so that everybody on your local area network can share that one connection. So here's an example of my own home router. I happen to own a Netgear wireless N300 router. It's not very new. I've had it, I don't know, at least 5 years, maybe even 6 or 7 years. I connect to the internet via the local cable company from where I live, which assigns an IP address to my wireless router. At the time that this PowerPoint slide was being written, the IP address for the internet on my router was 184.56.208.98. That's an IPv4 address. And then it administers a local area network just for my home with an IP address for itself of 192.168.1.1 and a subnet mask of 255.255.255. So I could connect up to 254 devices to my local area network. I don't have that many yet. However, if I invited 254 students over here and all of them brought their smartphones, they'd all be trying to connect there. We'd probably run out of connection space. At the moment, I have my Windows PC, my MacBook Air, my phone, my wife's Windows PC, my wife's phone connected to the local network. At other times, I sometimes have my school-issue computer turned on, or my iPad might also be turned on. Or maybe somebody's visiting me and they've got a laptop or a phone. So my local area network has a handful of connections at any time that share one internet connection. Now, here is a very nice theoretical framework called the OSI reference model, Open Systems Interchange Reference Model. This reference model says, there can be an awful lot of protocols just to get physical connections together, to package things up, send them along, and back in I think the OSI reference model first made its appearance in the early 1980s, about 1983, if I'm recalling correctly. It said there should be 7 different layers of protocols. You can think of this as physical layer, a wire connecting one host to another host. But the data on there has to be packaged up into the data link layer. So maybe that would be your Ethernet connection. But that data has to be packaged up into other packets that have your network layer protocol. Then that gets packaged up into transport layer and session layer and presentation layer, application layer. And they had definitions of what all of these would mean. Really nice theoretical model. It would mean that this data would get wrapped in an envelope for this layer, which would get wrapped in an envelope for this one, for this one, for this one, for this one, for this one. You know what? It's great in theory. It's almost never used with all 7 layers. So the diagram is conceptual. Usually layers 5 and 6, session and presentation, are just completely ignored. In fact, the internet itself has a series of protocols that group 5, 6, and 7 all together with each other. It's a good model for showing how each succeeding layer builds on what was already implemented, and what we've covered so far takes us through the bottom 3 layers: the physical, the data link, and the network layer. So let's look at this. Here's the same OSI reference model. At the physical layer, this is how our computer's going to talk to each other with a wired, a wireless, and infrared connection. At the next, how are those physical signals grouped together so that they can get sent along whatever the transmission medium is. Some typical protocols here are Ethernet or Wi-Fi. IP version 4 and version 6, we talked about the addressing of that in our last video. Those are network layer protocols. UDP, Unified Datagram Protocol, and the Transport Control Protocol are the most common transport layer protocols. Those are both used by the internet, although almost all of the traffic on the internet uses TCP, not UDP. Now, we learned with IP, whether it's version 4 or version 6, we could come up with a scheme for computers to identify each other on a global basis. Now, how do we get some useful information to them? Not just some bits, but enough information that can be processed by a program, like a web browser, or a database engine, or your mail server, or a mail client. The most prevalent are User Datagram Protocol, so I think I said this acronym wrong on the previous page, User Datagram Protocol, and Transmission Control Protocol. UDP is faster, but it's somewhat insecure and not as reliable as TCP. Most internet traffic uses TCP, so that's the only one we're going to look at the details of. This right here is a nice little layman's understanding of what UDP and TCP are all about. It goes through an explanation of that makes it similar to a post office and how you get data from one place to another. I recommend you pause the video now and go take a look at this website. I've also posted this URL of the website on the GOA webpage so that you can get to it a little bit later on, so you don't have to type in all of this. I'm not going to go to it and have a video of me watching a video, so I'm going to go on. Now, The previous website, the one that hopefully you just looked at, described TCP as a protocol that required the two communicating parties to establish a connection first, then transmit data, then acknowledge that the data was received. Part of how this is done is with TCP ports. Now here's a YouTube video explaining ports and firewalls. Go ahead and pause now and watch this YouTube video. Again, I've posted this URL on the GOA webpage so that you can get to it even without finding the right spot in the video. So pause the video now, take a look at the YouTube video. Okay, we're going to come back to TCP and IP, but let's just finish the 7-layer OSI reference model protocol stack. We've talked about layers 1, 2, 3, and 4 now. Layer 1, your physical wiring. Layer 2, Ethernet or Wi-Fi. Layer 3, IP. Layer 4, TCP. Now, we're going to skip talking about the session and presentation layers and skip to the very top layer of the protocol stack, the application layer. This is who's actually reading the real data and what are they going to do with it. Some applications have specific protocols of data they need to see in a specific format in order to function properly. Having these protocols allows users to mix and match programs that can utilize the same data. For example, web pages are served up in hypertext markup language and get sent using the protocol Hypertext Transfer Protocol, HTTP. That means that you can write a web browser that understands that layout and get all of the data and not need to know anything about how the data got to you. You can just display the data the way your web browser wants to. Not everybody uses the same web browser. Some of you might be using Safari, some of you might be using Chrome, some of you might be using Firefox, and so on. But you can still look at the exact same web pages. Some of the application layer protocols, I'm just going to mention them here, but we're not going to go into the details of them. Hypertext Transport Protocol, used by web servers to package up the web pages, web browsers to interpret the information. FTP, File Transport Protocol, it's used to exchange files directly from one computer system to another. Not used as much as it used to be when the internet was there, but there was no World Wide Web. People had only rudimentary email packages. There was no Google Drive or Dropbox to share files, so they would FTP them from one computer to another. Some others, Telnet, remote host connections. Domain name service is an application layer protocol. Simple Network Management Protocol, SNMP, is one, and so on. There are more. All I want you to know is that they exist. We're not going to do anything with the details. So, how do these protocols work with each other? Now, here's a diagram that I took from this website, thegeekstuff.com, and it shows that at the link level, Wi-Fi or Ethernet, you'd have a frame header, a frame footer, and some frame data. The frame data is shown in green. So there's some information here about, hey, I've got this many bytes of data and I'm doing this type of parity checking, and maybe here's my checksum or whatever your protocol had. And then it packaged up this data. Well, what's this data? All of this data, the frame data at the link layer, is at the IP level, the network level, consists of an IP header and IP data. So what was data to link is both header and data to the IP layer. This IP header has the IP addresses of the source and the destination, a few other fields, and then its data that is packaged up. Well, what's its data? Its data consists of either a TCP or UDP packet, which has a header that might identify which port it's going from and to, plus the data. Finally, that data is what goes to the application. So you wanted to get this data to an application, it got stuffed in this envelope, which got stuffed in this envelope, or put in this truck, which got sent to this post office, which got it to you. Awful lot of overhead. You may be thinking you're sending 10 bytes of data. and you might have 80 bytes of packaging around that 10 bytes of data. Now, here's the layout of an IP packet. Here's the header. Right here is the header of an IP packet, right up until it says data. Now, this is listed as bits from 0 to, well, 32 bits across this row, 32 bits across this row, 32 bits across this row, and so on. This is a very nice website right here. Not only has this picture, but it describes each field on here, and you're going to need that when you do assignment 4C, which is going to be, I'm giving you a real IP packet, and you're going to have to tell me what is the version number, what's the source address, what's the destination address, and so on. You'll have to figure out from the internet header length where the data starts, because these options can take a variable amount of room. That's what this little symbol here means. This is 32 bits of data, 32, 32, 32, 32. This might be 32 or 64 or 96, so on. So you need to have this internet header length to know where the data starts. This data is the TCP packet. The data for an IP packet is the TCP packet. So let's see what that looks like. Here, 32 bits, 32 bits, 32 bits, 32 bits, and so on. It's got the source port, the destination port, sequence number, acknowledgement number, and so on. It's got some bits in here that tell you if it's an urgent packet, if it's an acknowledgement, if this is a synchronized bit, and so on. This is taken from this website, which explains every one of these fields. You're going to use these in an assignment. I'm giving you one packet that's got IP and TCP together, and you're going to have to tell me source and destination address, source and destination port, sequence number, length of the data, and so on. You're going to have to be able to parse this stuff out. So, assignment 4C, with an assigned partner. This is going to be the same partner you used for 4A. So there are 9 sets of 2 partners each. You're going to look at some sample TCP IP packets. Actually, it's only one. From this, you're going to use the IP header to find the source and destination IP address, the length of the data, and then use the TCP header to find out the source and destination port, the length of the data in the TCP packet. Maybe you look at some flags in there. You're going to do that. I've got 7 pieces of information you need to find out, so you're going to extract 7 values and just submit 7 values. Simple. Then, the 2 of you have to schedule a joint Skype session with me. So I need a Skype session that has both partners and me. You're going to have to come up with a few times that you think work for the 2 of you. Now, not all of you are going to be in the same time zone as each other, so be considerate to each other. You know, if one of you is located 8 hours different than another, don't make the time be something that's 2:30 in the morning for one of the partners. Some of you are going to have to do some compromising. Then, pick 3 different times on 3 different days that you could make it, and send me an email and says, hey, we picked Tuesday at this time and Wednesday at this time and Thursday at this time, and I'll see which of those I can make. Now, I might be in school at some of those times, I might be asleep at some of those times, I might be Skyping with someone else at some of those times, and so on. So give me a few choices, and give me choices at different times of day, so that it's much more likely that we can get this done. Only going to be a 15-minute Skype session, and you'll explain to me how you got your data and prove to me that you know what's going on. Okay, everybody got it? Good luck. Go take a look at all of the websites that you need to look at, open up assignment 4C, get in touch with your partner, and get going. Thanks.